Hi guys, these are our notes for finding the inverse of a radical function, and we learn a little bit about one-to-one functions. So first off, you want to put your title up at the top of your page. Notes, radical inverses is all I put. The essential question you don't have to write down, but at the end of our notes, we want to be able to answer, what will the inverse of a radical equation contain? What are the steps of finding the inverse? What is a one-to-one function? And how do you restrict the domain so that a function inverse exists? So first, let's talk about finding the inverse and what the inverse of a radical equation will have. So the way that you reverse a radical is using an exponent. So our equation is going to have an exponent that matches the root's index. So finding the inverse, we're going to say to cancel or to reverse a root, you use an exponent. So the inverse will contain a power that matches the root's or the radical's index. Which is the little number that's at the outside. It's like a little tiny, it's kind of like an exponent, but it's in front of the radical. That's the index. We're going to write down some steps that you guys can use when you're working on your homework. The first step is always to go ahead and switch x and y. I'm leaving out the first step that we have done before. You just need to remember that f of x is equal to y. Step 2, you're going to go ahead and move any adding, subtracting, multiplying, dividing that is outside of the radical. Then you're going to raise both sides to a power that will cancel the radical. Once the radical's gone, you should go ahead and be able to just solve for y. And the last step is just to go back to function notation and replace y with f inverse of x. Or g inverse of x or h inverse of x, whatever the original problem had. All right, we're going to do a few examples of this. We are going to need our workbook, Unit 4A, for one of them. We're going to do like 3 examples. So our first example says f of x equals 3 square root of x plus 15. So I'm going to follow these 5 steps right here. My first step is to switch x and y, but I don't have a y. This f of x is my y. So when I switch, I get x equals 3 square root of y plus 15. Okay. Step 2 is to move any adding, subtracting, multiplying, dividing that's outside the radical. So this is my radical piece. I need to get that by itself. So there are things outside. There's a 3 outside and there's a plus 15. So remember, we're working in reverse. So to work in reverse, I'm going to go ahead and subtract 15 from both sides. I get x minus 15 equals 3 square root of y. Still trying to get that radical y by itself, so I'm going to get rid of the 3. The way that we undo multiplying is we divide. When I look at these two pieces, one of them can be evenly divided by 3, so I'm going to go ahead and divide both by 3. That gives me 1/3 x minus 5 equals the square root of y. All right, last step is to go ahead and, or not last step, but the next step is to raise both sides to the power that will cancel the radical. So since this is a square root, I use a square on both sides. So see how there's multiple pieces over here? I'm going to go ahead and put parentheses around them and raise that to the power of 2. So these guys cancel. Step 4 is to solve for y. The y is going to be the only thing under the radical, so I already have it solved for. I don't have to do step 4. I'm going to go to the replace y with f inverse of x. So it'd be f inverse of x equals, and then I just put parentheses, 1/3 x minus 5 squared, We don't actually have to multiply it out at all. We just leave it as the square. And that's my answer. Let's see. Next piece is, or next example, I have number 2. G of x is the 4th root of 2x plus 1. So again, step 1 is to go ahead and switch x and y. So this is my y. So when I switch, it becomes x equals the 4th root of 2y plus 1. Step 2 is to move anything that's outside the radical. So this is my radical. It's a 4th root of 2y. So the piece that's outside is this plus 1. That's the only thing I need to move first. So I'm going to go ahead and subtract 1 from both sides. So I get x minus 1. I'm putting in parentheses because they go together. They're holding hands. There was something else I had to do. Because now, in order to get rid of this 4th power, or 4th root, I have to raise both sides to the 4th power. So I put it in parentheses because both pieces are getting raised to the 4th power, but they're stuck together. It's not separate. So these things cancel each other out. I have x minus 1 to the 4th power equals 2y, because my radical went away. Step 4 is to solve for y. So there's a 2 in front of it this time. The last one didn't have anything in front, but this one does. So I have to divide both sides by 2. I cannot actually divide either of those pieces because exponents come before division. So once I, have this piece canceled out, then I have y by itself. I can go to function notation. This is g inverse. So you could either write it as x minus 4 squared all over 2, or you might see it written as like 1/2 x minus 4 squared. This is one way that you could see it, but this way is fine. You can leave it as one big fraction, but you could also see it as a 1/2 because technically there's a 1 in front of here. So they would write it as 1/2 parentheses x minus 4 squared. This would be in like vertex form of a parabola. Okay, one more example of this, and you guys are going to have some problems like this on your homework. I'm going to talk about one-to-one functions after. So I need you to grab your workbook unit 4A. This is workbook 4A, and we're on page 20. We're going to do 2 examples from this. All right, example 2 says find the inverse of the radical function f of x equals the cube root of x plus 2 if it exists, and determine the domain over which the function exists. We're not going to do this part yet because we haven't talked about it, but we'll just leave it. Okay, so we're going to follow our 5 steps. First step is to switch x and y. So I have x equals the cube root of y plus 2. Step 2 is to move anything outside the radical. So this is my radical piece. There isn't anything in front of my radical. There's nothing outside my radical, so I don't have anything to do for step 2. Step 3 then is to go ahead and raise both sides to the power that would cancel. Since this is an index, this number right here is an index of 3. I'm going to raise both sides to the power of 3. I don't have to have any parentheses or anything around that because it's just one piece. So I have x cubed equals y plus 2. Then I'm going to go ahead and solve for y. Step 4 is to solve for y. To get it by itself, I just have to subtract the 2 to the other side to cancel it. And y is officially by itself, so we can go back to function notation. It would be f inverse of x, because that was the original name was f. And then I just have x cubed minus 2. And that's it. All right, now let's talk about this domain over which the function exists thing. So I haven't talked about that part yet. So let's go back to our notes page, okay? This is going to be one picture, everything we did so far, so you can either like draw like a line under there, you can flip your paper over, but the next thing we're going to talk about is one-to-one functions, okay? So one-to-one functions. A one-to-one function means that both the original and the inverse are functions. So both the original and inverse are functions. Something that you might remember from Integrated Math 1, the way that you tell from a graph if a graph is a function or not is that it passes the vertical line test. So to be a function, you just have to pass the vertical line test. That's it. To be a function, you pass the vertical line test. To be a one-to-one function, that's like a special function, right? To be a one-to-one function, you have to pass both the vertical and horizontal line test. So the original passes the vertical and horizontal line tests. So first you're going to start off by drawing an original graph. So on your paper you're going to write original graph and then restricted domain, and then you're going to draw 3 little x and y axes. Let's go ahead and draw that real quick. You can pause. So our original graph, we're going to go ahead and draw a quadratic. We're going to draw a parabola. So I'm going to draw my parabola. Okay, here's my parabola. So if I was to do the vertical line test on this parabola, okay, so the vertical line test is where you take a vertical line and you sweep it across your whole graph and it only hits at one point, right? Okay, so this is the vertical line test. It only hits at one point. That means it passes, right? Passes vertical line test. But if I was to do a horizontal line test, it's going to hit twice. That means that it fails the horizontal line test because it hits twice. Well, what we can do is something called restrict the domain. Okay, this original is a function, but it's not one-to-one. So to make it a one-to-one function, we restrict the domain and we only look at part of the graph. So here's how we do the domain restriction. You look at what the turning point is. So parabola only has one turning point. It's possible it has 2 turning points or 3 turning points depending on what the exponent is. If it's a power of 3, it could have 2 turning points. If it's a power of 4, it could have 3 turning points maximum. Remember, the maximum number of turning points is 1 less than the degree. So since this is an x squared, then this is could only have 1 turning point. So what you do is you look at the coordinates of your turning point, and you use the x value and you restrict the domain, because domain is your x values. Okay, so when you restrict the domain, you're restricting the x values. So you look at what the x is. So if I only used the left side of the graph, or I only use the right-hand side of the graph of my parabola, then this would pass both the vertical and horizontal line test. So you use whatever the x is for your turning point and you restrict the domain. Here's how you're going to write your restricted domain. What you'll do is you'll put, if it's a parabola, okay, so this arrow right here, means it just keeps going forever. Well, this direction, because we're talking about the x direction here, this is heading towards negative infinity. So this is your x, right? This is your x. This direction is heading towards negative infinity. This direction is heading towards positive infinity. So on your little graph, the way that we would write our domain for this one is we would put a parentheses. This is called interval notation. We'd say negative infinity to whatever your x was, right, for this point, x comma y, whatever it is. And then on this, for the x, I'm sorry, I shouldn't have done that. For our x, you're going to put a bracket on the other side. What this means is that a bracket means like a closed circle on the graph, and a parenthesis means like an open circle on the graph, or a greater than or equal to. This would mean like an or equal to. This would be like a greater than or less than. So you can never actually be equal to infinity, but you could be equal to the x. And on this side, it would just be the x going towards positive infinity because it's on the right-hand side of the graph. We're going to look at another example of this, so hopefully I can explain it a little bit better. But sort of in words, you're just going to go ahead and use the x value of the turning point. Points could be more than one. Use the x value of the turning points and arrows towards infinity. Or I'm just going to say to cut the graph into pieces, I guess. I'm going to show you another example of this. Okay, but what you do is use the x value of the turning point or points to cut the graph into pieces. Okay, so we're going to go to bed. This is going to be another picture for your digital notebook, but we're going to go back to that page 20 that we were on earlier, and we're going to go to example number 4. So it says graph the cubic function f of x equals x cubed minus 4x squared plus 3x and determine the restricted domain or domains over which its inverse exists. So we're going to graph this function. We're going to go ahead and just use Desmos, but we are going to make like a little quick sketch of it onto our paper. Okay, all right, so I just took a screenshot of it when I put it into Desmos earlier. So here is what the graph of it looks like. I have 2 of them. It's kind of confusing. So here's my graph. So what you want to do is you want to identify your turning points. When you click on these points on Desmos, it will give you this point right here. So that's what you need. So you just click on whatever the turning points are. This is a cubic function. You're just going to go ahead and click on whatever the turning points were. Okay, so you're going to use the x's here. Okay, there's 2 turning points, so you're going to have actually 3 pieces that you're going to cut your graph into. Okay, you're going to cut your graph into this piece right here. This piece is 1 to 1. Then you're going to cut your graph into between those 2 turning points. That's parts 1 to 1. And then you're going to cut your graph into this right-hand side. That part is also going to be 1 to 1. So what you're going to do is you're going to go ahead and sketch this real quick onto your example page. So just has to be like a little quick sketch, nothing crazy. It kind of looked like that, I guess. This first point was at 0.451 comma something. We don't really need that part so much. Then the x portion of this one was 2.215 comma whatever the y was. We don't really need that part. We just need the x part. So again, you're going to cut it into 3 different pieces. So we'll I'll kind of color code it so you guys can see. So I'll do this yellow piece first. Okay, I'm going to write that as a interval notation. Okay, so the way that we would write that using our interval notation is use your x, and then this arrow, right, is pointing this left side of your graph. This left side is negative infinity. This right side is positive infinity. It doesn't matter which way the arrow is pointing. We don't really care about which way the arrow is pointing. We just have a left side of the graph and a right side of the graph. So this one, you're going to put a parentheses always for that infinity. So it'd be negative infinity, comma, and then whatever the x value was. So 0.451, and then you put a bracket. That's like an or equal to. We can be equal to that point. Then we're going to do that middle piece. So the middle piece is this one right here. This is a 1-to-1 function. So the way that we would write that one is we're going to use the 2 x values because we're in between those 2 points. So put a bracket, 0.451, comma, 2.215, bracket. And then our last piece, our third piece, is this piece right here. And that one is also 1-to-1. Right? Because passes the vertical and horizontal line test. So you're just breaking it into pieces wherever the turning points are. So you'll use your turning point is 2.215, and then this side, the right hand side of the graph is infinity, and infinity always gets a parenthesis. Okay, so if it's an infinity, you do a parenthesis. If it's one of the numbers, you're going to do a bracket. Okay, so we cut it into 3 different pieces if there's 2 turning points. So however many, I'm just going to draw like a random graph. However many turning points there are, you're just going to cut it at whatever those turning points are, and those are going to be your pieces. So you have like a piece here, and here, and here, and here, and here. Okay, so you'll just have that many pieces. So this one I have 1, 2, 3, 4, 5 different pieces because there's 4 turning points. So however many turning points there are, you're going to have one more piece than that. Okay, all right, so let me show you where these notes are going to go in your digital notebook for today so you don't have to fill in your table of contents. We already have that right here. Slide 11 and 13. So you're going to put the first part of your notes on slide 11. Slide 12 is going to be where we talked about one-to-one functions. And then example 20 is going to go on slide 13. Your homework tonight is on Delta Math. Okay? All right, go do your homework.